Next, we'll extend our discussion of population mean and variance by looking at the Gaussian distribution. Here we will discuss the relationship between probability and statistics. To do this, we need to assume a particular distribution P to characterize the behavior of the population of X. We saw some distributions in the previous table. To develop our relations, though, we'll use the normal or Gaussian distribution. A lot of the existing theory of statistics was developed using this distribution. It's particularly suited for describing the behavior of the continuous random variables common to engineering measurements. The normal distribution predicts that the scatter seen in the measured data will be distributed symmetrically about the central tendency. Its shape is the familiar bell curve, as shown here. The probability density function for a random variable x having a normal distribution is defined by this equation, p equals 1 over sigma over square root of 2 pi, with the exponent taken to minus 1/2 x, the value of the measured variable, minus the mean squared over the sigma squared, where x prime is defined as the true mean and sigma squared is the true variance of x. Here, p depends on the specific values of the mean and the variance. A maximum in p of x occurs at x equals x prime, the true mean value. This indicates that in the absence of systematic error, the central tendency of a random variable having a normal distribution is toward the true mean. The variance reflects the width or range of variation in p. Given the probability density function p, how can we predict the probability that any future measurement will fall within some stated interval of x? The probability that x will assume a value within the interval x prime plus or minus delta x is given by the area under the curve of p, which is found by integrating over the interval. Thus, the probability is given by the integral from x prime to minus delta x to x prime plus delta x of p, the probability density function, over dx. This equation is made a little easier by a transformation. If we define beta as x minus x prime over sigma, we call that the standardized normal variate for any value x. We can define z1 is equal to x1 minus x prime over sigma. This is the z variable. It refers to a specific interval on p, the probability density function, between x prime and x1. It follows that dx equals sigma d beta, and so this can be written: the probability between minus z1 and z1 is equal to 1 over square root of 2 pi, the integral from minus z1 to z1, of e to the minus beta squared over 2 dB. Because for a normal distribution, p is symmetrical about the mean x prime, we can write 1 over square root of 2 pi, integral of minus z1 to z1, e to the minus beta squared over 2 d beta is equal to 2 times half of that quantity, integrating from 0 to z1. The value in brackets is called the normal error function. The value, the probability of z1, is typically tabulated in a z-table. This integral is one-sided, so that means it's evaluated from 0 to z1. So the normal error function provides half the probability as expressed by the normal error probability equation. Now, we promised not to get into theoretical statistics and probability, but it's impossible not to get to this point where we can look at the z-score table without understanding some of where it comes from and using some of the integral math previously described. Here we see the z-table, which tabulates the probability of values for that, quote, normal error function, which is a one-sided integral solution for a normal variable for the probability from 0 to z1. z1 is defined as some measured value x1 minus the mean over the standard deviation. It's the one-sided integral giving us the probability of z1. The probability that some ith measured value of x will have a value between x prime plus or minus z1 delta is 2 times the probability of z1 times 100. We see the meaning of this visually in the normal distribution shaded in the bottom, from 0 in the middle, the mean, to z1. The shading represents the integral, or the probability, from that range from 0 to z1. So we define xi is equal to the mean plus or minus z1 times sigma. We define that at some probability p. Let's take a look at an example of these applications in practice. Consider a product packaging scenario. A recreational gear outfitter makes a large batch of newly designed ultralight hammocks. The overall length of the entire population of hammocks when stuffed into a sack has a known mean value of 6.1 inches and a standard deviation of 1.0 inches. Measurements are characterized by a normal distribution. Before setting up a machine, their packaging supplier requests an estimate of the range of stuffed hammock sizes containing 70% of the population of hammocks. The solution to this begins by using the z-value that we previously mentioned. For the product packaging problem, we know the population mean x prime is 6.1 and we know the standard deviation sigma is 1.0. We need to find the range of x in which 70% of the measurements should fall, and we're going to assume a normal probability density function. Formally, the solution starts with identifying that we're looking for the interval x prime minus z1 times sigma is less than or equal to xi less than or equal to x prime plus z1 sigma at some probability p%. We can transform that formal definition with the z-score to say that we're looking for the probability from minus z1 less than or equal to beta less than or equal to z1, which is equal to 2 times the probability of z1 from the one-sided table 4.3. That probability of z1 formally with the integral is 1 over square root of 2 pi, 0, integral from 0 to z1, e to the minus beta squared 2 dB. But we don't need to solve that integral since it's already provided in the table. What we're seeking here is the range in which 70% of the values fall. Because the z-table is one-sided, we only really need to seek half of the 70%, or 35%. So we scan the z-table and we look for the value where the probability is closest to 0.35. Then we see a value in the middle of 0.3508, very close to 35%. And then we just look up the z-value. The main z-value is 1, and then we look up and see 0.04. The z is 1 plus 0.04, or 1.4, with a probability of 0.35. So from that, we need our mean and standard deviation to define the range. Our range is the mean minus z times the standard deviation, 6.1 minus 1.04 times 1, which is 5.06, to the mean plus 1.04 times 1, the mean plus the z times the standard deviation. So ultimately, for 70% of our data, we find that the range is 5.06 to 7.14 inches, which is the value that our product packaging supplier requested. Let's take a look at another industry example, a compressor problem. The pressure in a line downstream from a plant reciprocating compressor is known to maintain a mean value of 12.0 bars. It has a standard deviation of 1.0 bar based on its history under normal operating conditions. A manufacturing engineer wants to implement a new process sensitive to high pressures exceeding 13 bar. She wants to know what is the probability that the line pressure will exceed 13.0 bars during any measurement. This compressor problem is similar in many ways to the prior problem. We're going to use the z-score for our solution. In the previous problem, we were trying to find the range for a given probability, 70%. In this problem, we're trying to find the probability for a certain range, and the range is a value over a certain pressure. So we know that we have a population, and from the population, long history, we have the mean is 12.0 bars, and we have a standard deviation of 1 bar. We're trying to find the probability x greater than 13 bars. We assume that that comes from the need to identify whether or not we'll pursue this process if the compressor will exceed this value, which could hurt our downstream process. We assume the normal distribution. So we first compute Z1. Z1 is just equal to the value minus the mean over the standard deviation. The value of interest is 13, our threshold, minus 12, the mean, over the standard deviation 1. So Z1 is equal to 1.0. We look that up in our Z table, and we see that the probability of 1 is 0.3413. So that's actually the shaded area in our plot. We need to find the probability greater than that value. So the probability greater than Z1 is equal to 1 minus 0.5 minus 0.34, or 16. So where do we come with the 1 and the 0.5? Well, the entire probability under the normal curve is 1. And the Z function deals with half, or the normal error function, one-sided, half of the probability, or 0.5. So we got 1 minus 0.5, and then we subtract off the shaded area, which is 0.34. That leaves us with the tail on the right of 16, 0.16. That indicates a 16% probability of a pressure exceeding 13 bars. Now what do we do with that? We need to make a decision, and the operator has to decide if that's too high a probability for risking whatever process that's sensitive to higher pressures, or whether they can live with that higher probability, It all depends on judgment at this point. In the next example, we'll look at crash test failure. An automaker questions negative results of a crash test at a national insurance lab when they realized that impact results were compared with an inertial model that relied on a gravitational constant determined from a ball drop experiment. Specifically, they learned that the lab's gravity experiment was conducted by an engineering summer intern who estimated the acceleration due to gravity at 9.5 meters per second squared, with a standard deviation of 0.1 meters per second squared experimentally. But they know from physics principles that the true value of 9 is 9.8 meters per second squared at this altitude for gravity. They want to determine the probability that the intern's gravity experiment results were due to random chance or random error alone. Of course, if the experiment was likely to be a blunder, they will argue against the mandatory recall of the vehicle in the crash test. In this problem, we have experimental data that was surely to come from a sample. So we have a sample mean of 9.5 meters per second squared, plus or minus a sample standard deviation of 0.1. But we know the true mean value is 9.8. So for this, we compute a z value as 9.8 minus 9.5 over 0.1, or 3. We then define the probability minus 3 less than or equal to z less than or equal to 3, which is equal to 2 times the probability of the z value of 3. We looked that up on the z table, and the probability of z is equal to 0.49865. So the probability then is 2 times 0.5 minus 0.49865, or 0.0027, which multiplied times 100 is a probability of 0.27%, a very low number. This very small probability of random error indicates that we likely had a systematic error, given the 0.3 meter per second all squared of the gravitational constant. Our next manufacturing example involves fiber production. Production of a certain polymer fiber follows a normal distribution with a true mean diameter of 20 microns and a standard deviation of 30 microns. A process engineer would like to compute the probability of a measured fiber diameter greater than the maximum out-of-control limit of 80 microns. It would also be informative to estimate the probability of a measured diameter between 50 and 80 microns, a range within acceptance but considered indicative of borderline performance. In this problem, we know the true mean and true standard deviation. The true mean is 20 microns, and the true standard deviation is 30 microns. And we're asked to evaluate the 80 micron value. So to do that, we can first compute the z statistic. Z1 equals x1 minus x prime, the true mean, over the standard deviation, sigma. And we get a z1 of 2.0. So from our z table at 2.0, we see that the probability is around 0.4772. Since we're asking for the probability of x greater than 80, we have 0.5, half the probability of that normal error function, minus 0.4772, which gives us 0.0228. We'll multiply times 100 to get percent, 2.36%. So it's a very small chance that we have a probability of a measured value greater than 80 microns. Next, we're asked to find the probability between 50 and 80 microns. Again, we use the z-table. In this case, with the x2 value of 50, we find the z is 1.0, and we can look up the probability from the z-table of 0.3413. In that case, we have the range, the probability of 80 minus the probability of 50, 0.4772 minus 0.3413. This equals 0.1359, or 13.6%. There's roughly 14% probability that a filament measures between 50 and 80 microns. What we decide to do with that information depends on the context and the problem at hand.